Hey guys, welcome back to the PX4 Developer Summit. I got your next speaker lined up, and the next presentation is called Automated Testing as part of the PX4 Development. Our speaker is called Julian Kent. He's calling in from Zurich, Switzerland. He's a senior engineer at Ethereum, where he coordinates the robotics-focused activities, balancing core feature development with supporting Ethereum customer integration work. He also lends his expertise in electronics, software, and hardware design around the company as needed. Jack of all trades. This session motivates the use of automated testing in PX4 of all types and explains which types of testing should be used in what circumstances. Julian will show you how to implement unit and functional testing with GTest and as a kickoff point for new contributions. Please welcome Julian Kent.
Thanks for the introduction, Ramon. Today, we're going to be talking about automated testing as part of PX4 development. Now, I have a quick overview for you. We're going to start with what is automated testing, because of course, this isn't a topic that's familiar to absolutely everyone. Next step is my motivation for automated testing. And to me, this is the most important part. In PX4, we now have the technical parts to get the automated testing working. What we really need is the cultural stuff, and this needs to come from everybody. This is community members, this is core developers, this is OEMs, everybody. So for me, this is really the core part. It's the extra work, yes, but why automate? We're going to go through a few steps of how to do this in practice, and then I'm going to end off with a demo, and hopefully that'll work just like Jonas's one did in the presentation just before. So we'll start with what is automated testing. And while I'm sure most people are familiar with the process of manual testing, that is, you write some code and afterwards you go and you check whether it works. There's actually a lot of stuff here, a lot of different layers of automated testing that you can do to make sure that your code really works and that end users get the best code and that you have the best developer experience. Now, the first one is unit testing, and this is very low level, one function at a time, one class at a time. You check that that has exactly the behavior that you wanted it to have. And this is really for you, for the developer, to make sure that you implemented the thing that you wanted to implement and that your idea is actually captured in the code. The next step is functional testing, and this is a higher level. This is with multiple classes working together. This is maybe passing messages backwards and forwards or one library calling into another. This is to make sure that they work together, that the one library, when it calls into the other, gives it the right type of data or these kinds of things. In PX4, we have UORB messaging, and this is included in the PX4 functional testing libraries. The next is integration testing, and this is usually with a full system. In web development, this would be calling fake servers with your actual data, or putting your data onto a fake server and calling it and checking that it's working. In PX4, this is something like CIDL testing, where you run your whole system in a simulation. And basically, this covers everything except for the specifics of running on the actual hardware target. Then finally, we get to the manual testing, which I think everybody is familiar with. And that is the user, this is in the testing world known as user acceptance testing. And this is where a real human tests it, often on real hardware. And especially for us with drone development, if something goes wrong here, this can end up being quite expensive. If things, you can end up with broken frames. But even if something doesn't go horrifically wrong, this is also expensive because it's taking up users' time every single time something like this needs to be done. So now that you have a brief background of what these different types of testing are that I'll be referring to, let's go for my motivation about why it's so important. So the first step is that development with testing is maybe unintuitively a lot faster. And that is because you get feedback on whether your code works a lot sooner. To go back to the previous example with if your code goes all the way to a user before you know if it works, that can take days to get a response, or months, or something like this. Whereas if an automated test runs, you can have your results in seconds. Now, if this can actually have a big improvement for developers as well from another perspective, in that you haven't forgotten what you're working on and all the very low-level details when you get to the automated test, when you get to the results of whether your tests are working. So this means that you have a full, in your mind, every little detail, and when you get that feedback that there's a bug here, or maybe it's not a bug, but maybe it's not doing exactly what you expected it to do, you can have your full mental model is still there, and you get really quick feedback cycles. This makes less bugs get introduced as well during the bug fixing, and it's less development time in total. So the next one is, let's try to split human work and computer work and make computers do work that computers are good at and humans do work that humans are good at. So computers are good at running code, and they're good at comparing outputs. Humans are good at pattern matching, creative thinking, and problem solving. So if you're thinking about checking whether code runs correctly, this is very obviously a computer task. It's you run the code and then you compare the output with the previous time the code ran or with what the specifications were for the code. Whereas for humans, designing the tests is writing specifications and writing code, and this is something that computers are not good at. Next reason for automated testing is that tested code is reusable code. If you have code that is completely untested, or that tests are only done at a very high level, then you cannot reuse the lower components of that code because they'll probably not be architected in a way that allows them to be run in isolation without all of the pieces around them. So if you only have CIDL tests, then this means that you'll probably only be able to reuse your code across different vehicles. And this means taking the entire flight controller as a stack. Whereas if you have unit tests, if you have functional tests, you can take whatever those units or whatever those functions are and pull them into other areas. And this means that you can, and this is entirely due to the way, because the tests point to the code, so you have to have your code architected in a way that multiple things point to it via a well-defined API that your tests actually specify what the behavior is. So this means that the interface of the tests and the interface of the system is very similar, and so this works quite well. A next step is low-risk refactoring. If you have already quite a few tests in your system, then if you refactor and you broke something, probably a test will fail. And this is much quicker to find out than putting it on a vehicle and trying to fly it, and then the vehicle crashes. And then this is more to make the maintainers' lives easier. If you have untested code that is under active development, you end up with more bugs. If you have untested code that is not under active development, this code is hard to maintain because it's probably not specified or documented very well exactly how it should behave. Whereas if it was tested, it would be easy to maintain because the tests say exactly what the code is meant to do. And if you had tested code that's under active development, fewer new bugs. And then when we come to industry outcomes, on the right, I've got here a study from 1985, and I've actually left out a bunch of the different types of testing and design reviews that they've gone through. But they've said that roughly 25% of bugs are caught in unit testing, and they actually said it was between 20% and 50%, and more are caught in functional testing, more are caught in integration testing, and then in-field testing and code review both catch about 50%. However, the cumulative effect of having all of these different layers of testing and review add up to around 99% of bugs. So if you're only doing some of these, you're probably not going to catch as many bugs as you could be. And if then this ties in quite well with here in how many actionable feedback cycles do you get per hour. With a unit test, if something breaks, then you know almost down to the line what is broken. With a functional test, you probably know within 100 lines where the bug is. Integration tests, it could be pretty big. And in-field tests, it could be even hardware that's a problem. You don't know. So, and code review, oh, you can only do 1 or 2 of those an hour, right? So it's really, there is a trade-off here between how many bugs you catch and how quickly you can get feedback and how specific that feedback is on exactly the type of bug. And just to give an example of the type of things that high-level or in-field testing might not catch, but a unit test would catch, is something like a controller that is clamping its inputs because the inputs are wrong. And you would never find that out if you didn't have a unit test, and the functional and in-field tests, or the in-field testing and integration tests, would probably pass, but you'd have reduced performance. And this is something where the unit testing would give you that better performance, even if technically at the high level it was working, if not very well. So who benefits from unit tests? And I didn't put this on the overview because I wanted to surprise you with it. Everyone benefits from unit tests, and everyone benefits from functional tests. Everyone benefits from integration tests and in-field testing. More testing is better, right up into the point where we stop finding any bugs at all. And I think that's a very, very long ways away for basically all software that you've ever met. So community contributors, they are less likely to introduce new bugs into the software if their code is tested, and the maintainers like that as well, and because they are less likely to have bugs, so they're more likely to review it and merge it quicker. And also this means that your code is less likely to break in the future when changes happen. The core developers, more tests in the code means it's easier to maintain, and the bugs tend to surface before it gets to end users. And this really means that less bug reports, and the developers can deal with the problems themselves instead of having this giant loop around to end users. Manufacturers, you deal with less bug reports from your end users. If you have custom features that need to be developed, they can go quicker. And new airframe bring up, testing new things, putting things on real vehicles, chances are that the bugs already got caught on an earlier level, and so you're not going to have as many crashes, as many fried motors, fried hardware, broken whatever, lost customer trust. And end users, of course, they like less bugs, they like faster bug fixes, and they like more features, because remember, we can do more features in the same time when we have tests. So in practice, how do you make this really, really happen? I'd like to go over a few places here where automated testing 100% makes sense. If you have new code, write unit tests for it, write functional tests for it. Write your tests as specifications. Make sure that your tests explain what your code is meant to do, and then test against that, check that your code is doing the right thing. If you have untested code and you don't know what the quality is like, you don't know how it behaves, write tests for it. You can then find out exactly how it behaves. You can give it any type of input you want, and you can make sure that it does the things you want it to do. If you have code that needs to be debugged because you think there's a bug in this test, in the code, there's a perfect place to write a test. Because often bugs are triggered by edge cases because, well, you don't usually write bugs on things that are working well, or find bugs in things that are working well, so it's going to be in an edge case. And these edge cases are on real vehicles, very difficult to reproduce. Maybe you have to have it at a certain time of day. Maybe you need your GPS to fail at the same time as you're taking off. Maybe you need some other strange combination of things. However, if you have some theory about what's triggering your bug, write a test. Make in your test, trigger that exact use case. If the thing breaks, your theory is correct. You now have a reproducible situation on your computer where the tests are showing exactly where the bug is. Now you can fix your code, and when your tests pass, you know the bug is gone. There are some cases where testing sometimes doesn't work. If you don't know what your code is meant to do, maybe you're trying to explore some new image processing algorithm and you just want it to look cool, but you're not exactly sure how to write what does cool look like, then great, maybe you don't need tests for that. However, you should probably still try to set up a quick feedback loop so you can very quickly get feedback on whether your code is doing what you think it is. Glue code is where you have a bunch of systems and your code just sticks things together. And in this case, putting code together, it can be a lot of pain to set up a test for something like this. I would still recommend having something that you can check that it at least runs and it at least thinks it thinks it knows what it's doing, even if you're not 100% sure. Testing, of course, you're not going to catch every single bug, but you should at least try to catch the easy ones. And the last one is your test code or your build code. Does that need testing? Probably not, unless you have something big that you're trying to do in your testing code, like you're trying to generate a whole bunch of sample data to test your other stuff with. Maybe you want to make sure that you're actually generating the sample data that you think you are. Otherwise, when your other tests start failing, you might be very confused. So zombies, surprise. There were zombies here, and this is actually an acronym. This is to help you remember what kind of tests you need to write. So the first one is 0, no data, null. This is try to test the simplest use case just to make sure that your thing gives you back probably something similar to what you gave it. Don't just set your test up, don't do anything, make sure that there's no surprises. The next thing is 1, just put a little bit of data in, check that it still works. Now you can build your test up to do everything that you think it did, that you want to do. You can add more tests doing all the functionality you want. Boundaries, catch your off by 1 errors. Make sure that you loop through every single element in your array. Make sure that if you specify that something should stop at a certain point, that it stops at exactly that point. Check right before and right after to make sure that it stops at the right time. Interfaces, make sure that your API does the things that it promises, and make sure that you are actually testing what your API promises and not some other functionality that your API isn't actually promising and that is maybe more specific to the implementation than the API. Exceptions, try throwing garbage at your code and see what happens. Make sure it doesn't crash, best case. Like, especially when you're working on high reliability systems like drones, we don't want our code to segfault, hard fault, whatever it is, and because that can lead to really, really bad outcomes. And then simple at the end. I think they needed an S here, so they added a simple. Just put up something simple and make sure that this works. Often this is the first kind of test that I do after the zeros. So when you're doing your testing, it can often fit into a framework we call behavior-driven development, where you use your test as specification for your code. We set it up with a given, when, then. So given the initial conditions of your code, we do when we do the thing we want to test, then you should get your outputs. And here's a real example, but I'm going to do a demo for you now with an actual real example. So in PX4, there's this function here, and my colleague Roman recently wanted to call it, and I said, oh, that looks like it's got nice inputs and outputs. It can very easily be used for a unit test. So this is going to be what my demo is. This is a waypoint from heading and distance, and this has existed in PX4 at least for 4 years. It hasn't been modified. So let's add a test for it and see how we go. You give it your latitude and longitude start, your bearing in radians, a distance in meters, your latitude target, and your longitude target. So let's copy that. Let's make a new test here. Waypoint from heading and distance. And let's start with our zombie acronym. So let's do 0 as a starting point. So let's start with our behavior-driven development, a given, when, then. 0 distance and varying from a starting point. When we call this, then it should give the input. So let's make a few things. So we have doubles actually. Minus 33, 18, No, these are floats. Okay, so this is our inputs. Now we need to call the function with lat start, long start. Let's see here, we have lat start, long start, bearing, distance, then lat target, long target. So long start, distance, okay. Why is this complaining? Ah, yes, I need to point pointers to these. Okay, now my function is happy. For those of you who are wondering, I'm using kdevelop as an IDE. It works really well with PX4. Then we have expect float equal. Lat start, lat end. Okay, so this is now a test. We've written a test, we've added a test. So let's run the test. We can just do actually, so if you go into ECL, you can do make test. And there, our test passed. Let's just make sure that it's actually working. Let's add a, you know what, let's make the distance minus 1,000 and check that our test fails. Oh, yes, it looks like our test fails. So let's go and see what it said. It said minus 33, and but what it actually gave us at lat end is minus 32.99. Now, I put minus 1,000, and the bearing is 0. You would think that if I gave minus 1,000, the latitude would go further negative, not go north. So that's a bit of a surprise there. If I do plus 1,000, do I get the same result? Yes, I get the same result. So now this is something that I would say is unexpected behavior from the test. And let's actually call this distance is negative. Now, this is actually something that I think we should fix. So if it's saying minus 1,000 and you're having a bearing of 0, that should mean it should go south, if not go north. So let's see what actually is happening inside of this function. There's the offender. It's taking the absolute value of the distance. That doesn't make much sense for this standard 2D projection type of function. So let's take that out. I'll check afterwards to make sure that it's not being used anywhere that's expecting that negative distance to be positive. But still, this is something that I think is unexpected behavior. And if it doesn't hurt somebody now, it might hurt somebody in the future. So now if we go back here and run the test again, now we get a more negative number when we did minus 1,000, which is exactly what we expected. So I will go back and figure out the exact transforms to get this into the correct values. But now you've seen how to make a test, how to write a test. And if you're doing it anywhere else in PX4, this is basically the same process. You will go in, you will write tests according to exactly the GTest, and there are also there's also in the user guide a fairly extensive way, and there are also examples that are there. Yeah, so questions? through the questions. So the first question is, do I have experience on using TDD in these type of platforms? Yes. I prefer behavior-driven development instead of TDD, but it would test TDD is test-driven development. I feel like test-driven development sometimes deviates a little bit from where from what the actual value is for the code that you're providing, and instead focus a bit too much on providing value to the tests instead of the code, which is why I like behavior-driven development, because you're doing it. But yes, I think behavior-driven development on these types of systems is very valuable, because you end up with something that is well specified, that you know exactly what it's meant to do. Do we have a system tracing standard? There is some stuff. I know that you can output stack trace or stack pointers on there's a high-speed bus, and this is definitely available on V5X. I'm not sure about others yet, and this can be used for profiling. And yes, however, I think for a lot of the development, a lot of at least business logic, things that don't involve drivers and things that don't involve actual hardware-based performance tests, where you're more interested in relative performance rather than absolute performance, I think a lot of it can be done on your laptop, cross-compiled, and not have to go through a difficult debugging cycle and special IDEs that can connect over JTAG and things like this. Yes, and any more questions, you can find me on Slack. I will be there to answer anything else you want to know. And I hope to see more tests in the future.